without having turned it on first. Okay, good morning, everyone. How's Thursday? I hope that's the case. I hope I might be reading a little into the sarcasm in your tone. At least that's what I detected. I hope today is good. First week of the semester is nearly done. I'm looking forward to the weekend. Any questions, issues, concerns, etc. before we get started today? Okay. Has anyone had any issues accessing Brightspace or WebAssign? Okay. If you haven't tried yet, please make sure to do so very soon, because if you have an issue with it, I need to know about it sooner to get it fixed sooner. So, last time was mostly syllabus stuff and the, I guess, prologue to the first unit that we're going to be talking about. That being, I start with thermal physics this semester, and we're starting off slow because I'm already thirsty. That's what that means. Stay hydrated and get plenty of sleep. So, we're starting off kind of slow. The first couple bits that we've talked about in this chapter should be review. If you're not familiar with thermal energy, you should at least be familiar with temperature. And that's going to be getting from one to the other, and then beyond that, it's going to be our goal for today and tomorrow. So, as a reminder, thermal energy is another form of energy. It's measured in joules, but just like all forms of energy, and oftentimes one of these mechanical forms of energy will turn into thermal energy due to some thermal process kind of creating it as, or turning energy into it as sort of a byproduct of friction. So literally everything you do is going to technically make you warmer, because every time you move your muscles or breathe or be a warm-blooded organism, which is all the time, you turn a little more of the stored energy inside of you into thermal energy. Now, this energy, like I said, is measured in joules, and it's different from the previous types of energy that you studied in 1500 in that it's even harder to see. In general, you can't see energy directly, period, because it has no physical presence. It's just something that matter can possess. But when matter possesses kinetic energy, elastic potential energy, or gravitational potential energy, you can usually somehow detect that with your eyes. Kinetic energy, it's moving. GBE, it is some elevation above some other point. Elastic, it is deformed in some way. Thermal energy, though, is harder to track with just your eyesight because it's basically internal energy. When something possesses thermal energy, it possesses it on the molecular level. So you can't see the energy itself, you can only see what happens when something has thermal energy. For example, when you add thermal energy to something, it might start glowing, or it might melt or evaporate. And if you touch it, odds are, ouch. So there are ways to detect its presence. As for what it does, when something has thermal energy, its molecules start getting scrambled. Now, the little dots on the screen, the circles, represent the atoms and the molecules that make up everything. And all of those particles have mass. And when they have thermal energy, they are moving around. The more energy the particles possess, the faster they are going to move around, and the more they're going to bounce off of one another. The hotter you make something, the more chaotic it becomes on the inside. Now, each of these particles has a velocity and a mass. Does that sound kind of familiar? They have energy, velocity, and mass. What might that sound? What's that sound kind of like? Sorry, a little louder? Or was someone just fixing it up? It's okay. So, kinetic energy is the energy of motion, and all of these particles have mass and velocity, therefore they have some amount of energy making them move. The more thermal energy that the matter that makes up an object possesses, the faster its particles are going to be moving around. Thermal energy is basically just kinetic energy, but on the atomic level. Instead of the whole object moving in one direction, its particles are moving everywhere, in every direction. And because they're constantly bouncing around inside of the object, that motion kind of cancels out and the object doesn't go anywhere. So thermal energy is an abstract form of kinetic energy, if that helps you to think about it. And because it's so similar to kinetic energy, these formulas are up here right now mostly to illustrate a point. These are not, we will eventually do some math with this, but right now it's just to illustrate the kinetic energy example. It's kind of hard to determine the kinetic energy of a single atom due to the fact that their masses are incredibly tiny, you can't see them with the naked eye, and they are moving at the same time incredibly fast and incredibly subtly, hard to detect, such that you can't really measure the kinetic energy of a single atom. So instead, we have come up with alternative ways of doing that. If we wanted to know the kinetic energy level of one atom inside of one object, say for example, we have a block of ice, and we just care about the kinetic energy level of this single H2O molecule. Sorry, yes, the kinetic energy, we just zoomed in real close, and this is one particle of H2O. If we wanted to know its kinetic energy level, we would need to know its mass and its velocity, which is nigh impossible to know, especially if you know anything about the Heisenberg principle. So instead, we came up with a different assumption. We're going to use this a little more later. Right now it's just to segue us from the energy overview into temperature. So, to find the kinetic energy level of an atom, multiply 2/3 times this constant. This is a constant. This is the only thing you'd ever plug in right here. So it's a specific constant for this specific formula. And then you multiply all that by the temperature of the object. So we tend to measure kinetic energy levels and thermal energy levels through measuring the object's temperature. Temperature is the way in which we kind of interface with the thermal world. But let's say this is a block of ice. Okay, I've already said this is a block of ice. What temperature is ice at? What is the temperature at which ice begins to exist?
0 degrees Celsius.
Very good. We got 0 Celsius. There might be another number floating around in your heads. Very good. 32 Fahrenheit. So if we want to use temperature, which one do we use? There's multiple ways of describing the temperature of this one object. They both describe the freezing point of water. Which one do you plug in?
Don't you technically need Kelvin?
You do technically use Kelvin. And in a moment we're going to start looking at the different temperature scales and why we like to use Kelvin. But at least to start with, if you plug in 0 Celsius into this formula, you'll get a kinetic energy level of 0. But I promise you, even at 0 Celsius, this object still has thermal energy in it. because it can be made to be even colder. It doesn't happen much in this particular state, but it regularly gets colder than this, which means objects at 0 Celsius can lose even more thermal energy to get even colder, which is why we don't use either of these scales super much in physics. Well, we use Celsius enough, but we'll probably never use Fahrenheit in this class, except in a temperature conversion question. So, we use temperature to help us estimate the thermal energy level of an object. And we have lots of different methods of measuring temperature and different scales of temperature. There was another point I wanted to make on this slide. Sorry. Back to it in just a second. Now, to make something hotter, one has to add thermal energy to it. So there's a physical thing that you add to the substance to make it warmer. What does one do to make something colder?
Take away.
You take away thermal energy, which means, on a technical level, and this might be a little bit hyperbolic, cold doesn't exist.
The absence of color.
Right. When you feel cold, you feel the absence of thermal energy. You add thermal energy to something to make it warmer, but there's nothing you add to something to make it colder. You have to take thermal energy away. Cold is the absence of heat. That's just a little technical detail that's worth knowing before we start doing problems where we track where thermal energy goes. Now, and the first time I heard cold doesn't exist, it took me a few days to wrap my head around it. So, we cannot measure, it is very hard to directly measure the energy level of a single atom, so instead we measure the temperature of the object the atom is in. Lots of different ways to do that. Typically, we use a thermometer, and the way that a thermometer works is you touch the thermometer to the thing you're measuring. Thermal energy will either enter the thermometer if it's a warm object or exit the thermometer if it's a cold object, and the fluid in the thermometer will expand or contract to indicate the correct temperature. But we have a couple other devices that'll do basically the same thing. And thermometers are interesting because humans tend to assume we have a built-in thermometer. You can usually tell if you can feel something and detect if it's hot or cold. But if you touch something, can you tell what temperature it is numerically? So humans, we can detect temperature differences, but we don't have a built-in thermometer. We don't have a way of actually measuring temperature. The cells that detect temperature are located right in your skin. And all they can do is respond to, I feel thermal energy leaving, I'm going to register cold, or I feel thermal energy entering, I'm going to register hot. You can usually measure a degree of warm to hot. Something can be pleasantly warm or it can be ouch. But it'll never just give you a number. We're not calibrated like that. And if it ever feels neutral, that's just the temperature that your skin is designed to insulate you to. You also have no temperature sensitive cells inside of you because inside of you is like 97 degrees, and yet room temperature air at 75 feels normal. So you don't detect temperature inside of you. You don't detect temperature at all. You just detect hot and cold compared to your skin. Because of that, temperature is always a comparative thing. Our temperature scales were made comparing one thing to another and calibrating from there. And because of that, they're all kind of wonky and subjective. There's 3 temperature scales that are going to come up most often in this class. They've all been mentioned out loud today. So Fahrenheit, Celsius, and Kelvin. And just to go through their history a little bit to explain why we have 3 of them. Fahrenheit is actually the first temperature scale ever developed by a man named Gabe Fahrenheit. He was a Polish scientist, and we needed a temperature scale, so he made one. In retrospect, it doesn't make a whole lot of sense because freezing is 32, boiling is 212, and there's 180 units between the two. I'm sure at the time it made sense to him though, because he didn't base it around normal water. It wasn't designed so that water would sit comfortably at some nice measurement. In the Fahrenheit scale, pure water freezes at 32, and sea brine freezes at 0. So, I don't know why he used sea brine. I assume he was a sailor or had something to do with the ocean often enough in his life for that to be an important detail. I also don't know, and the only reason he went with 180 units separating freezing and boiling with normal water is because that let him physically divide up his model thermometer into nice intervals of 6. So odds are the man has a very specific ADHD, and I can't fault him for that. But because this scale, in retrospect, is kind of wonky, eventually a man named Anders decided to make a new one. It wasn't originally named Celsius, it was actually originally named centigrade. Because centi means 100, and there's 100 units between boiling and freezing in the Celsius scale. So this was designed by Anders to be a little more metric and scientific community friendly. Freezing is at 0, boiling is at 100, nice even set of 10 of 10s in between the two. And for a long time, that became the standard scale that we used most of the time. But then we had the realization that 0 degrees Celsius ice can be made even colder. Therefore, colder temperatures exist. Therefore, Celsius is not an accurate measurement of the thermal energy level of an object. And that is where the concept of absolute zero came from. Has anyone not heard of absolute zero before? Okay. So, and to refresh your memory, if it's been a minute, absolute zero is the literal coldest anything can ever be, by definition. Pardon me. For something to be at a temperature of absolute zero, it has to have had all of its thermal energy extracted. And since thermal energy is what makes an object's particles move around randomly, an object at absolute zero is perfectly atomically stationary. There's no thermal energy, there's no random movement inside of it. It's basically frozen in time. Not just frozen in ice, frozen in time. It might as well be because nothing's moving until it gets some energy and you want to pause it. And you will never experience this temperature because if you somehow did, you'd be flash frozen into a weird time cycle, probably, and that would be the end of your existence, that would probably be the end of you. This temperature does not natively exist on Earth. This temperature doesn't even natively exist in space. This is largely hypothetical, but we've managed to use very powerful lasers to get single atoms to absolute zero in order to study the effects. But you can only get one atom to absolute zero by using lasers as a tractor beam to force it to stay still. And as soon as another atom touches it, it's going to warm back up. So, absolute zero experiments are still going on. All we know is it's hard to get here and things get weird when you do. But Oh, his name is here. The scale was developed by a man named William Thomson, who had the title of Lord Kelvin. I have yet to actually Google why he would do that. And the absolute zero scale is based on the Celsius scale. They're designed to be compatible with a 1-to-1 ratio. They just kind of offset it. So to get from Kelvin to Celsius, you just add or subtract 273. And because Kelvin is the best indicator of how much thermal energy something actually has, it's the one we use most often in physics and chemistry, and the one that we'll use most often in this class. And they all measure the same thing, so if you have a measurement in one of those scales, you can convert it to the other ones. This chart just sort of lists a comparison between them all. For the freezing point of water, 32 Fahrenheit, 0 Celsius, and 273 Kelvin. Humid body temperature, this is your internal temperature. This is what the doctor checks for to make sure that nothing's wrong with you. And boiling point of water. Again, notice you have 0 degrees difference here. Sorry, you have 100 degrees difference in Celsius and 100 units difference in Kelvin. If something's temperature increases by 1 Celsius, it will also increase by 1 Kelvin. They're a direct scale. Another number that would be good to know that is just not on this particular graphic is room temperature in each of these scales. Time to continue the time-honored tradition of physics professors at PC trying to dunk their dead markers. Sorry. And I never do it. Did not mean to scare you, sorry. Okay. Thanks, winter break. I'm going to stand further over here now. Oops. The other day down the hall, I think it was Dr. Owens was trying to, I had like 3 dead ones, and I just saw from the hallway like 3 different markers slide out of the hall as he missed the trash can. All right, room temperature. Typically, that's set about 75 Fahrenheit. Most commercial buildings, most houses that you walk into will probably be set to within 5 degrees of this. And usually that'll be the temperature air where you are not noticing it because it's neutral to the temperature of your skin most of the time. And because this is the average temperature of Earth, we consider it to be the average temperature for pretty much every experiment. So unless something states otherwise, most experiments will take place at these average temperatures listed. In Celsius, that lines up at about 25, which means that should line up with 298 Kelvin. A quirk you might have noticed in both the writing and also my speech, you don't have degrees Kelvin. I'm not entirely sure why Mr. Lord Kelvin made that decision, but there's no degrees symbol here, and I will never intentionally mean to say degrees Kelvin out loud. It's just Kelvin. Because he had to be special. Granted, it is the best scale to use, so it makes sense to stand it up. So, this is your first real formulas in terms of what you might see on the homework assignment, just converting between the different temperature scales. So, if you have a Celsius temperature and you want a Fahrenheit temperature, you use this, plug the Celsius temperature in here, you multiply it by the fraction 9 9/5, and then whatever you get from that, you then add 32. And just for the sake of order of operation, we usually put parentheses around those 9/5. You're multiplying the GC by the fraction 9/5. And just to prove this works really quickly, if you plug in a Celsius temperature of 0, 0 times 9/5 is 0, plus 32 gives you 32 Fahrenheit. Similarly, if you plug in 100 Celsius, 100 times 9/5 is 180, plus 32 is 212. And I like having this formula on hand, but sometimes you have a Fahrenheit and want a Celsius, and to save you at least a little bit of algebra, the inverse formula is 5/9 times, open parentheses, TF minus 32. So same formula, just re-engineered slightly. Keep in mind order of operations here. You need to subtract the 32 first, then multiply that result by 5/9. Questions so far? Okay. Kelvin's really easy to go back and forth between. You just add 273 to the Celsius measurement. Conversely, if you have a Celsius and want a Kelvin, if you have a Kelvin and want a Celsius, you would subtract 273 from it. So on the previous formulas, the 9/5 is to scale the size of the unit, because a Fahrenheit unit is just numerically bigger most of the time. So that's to scale the unit size, and then the 32 is to offset the freezing point of water. Here, you don't have to change unit size, there's no multiplication, it's just the offset. So, real quick, just a teeny tiny bit of practice, and you guys find these temperature scales for me. These temperature conversions, excuse me. I'll be right back. My office. you guys are wrapping these up. So there'd be a total of 6 numbers solved for. As you're finishing that up, brief fun fact, Kelvin will never line up with Celsius and Fahrenheit just because it's so offset from both of them. But there's one temperature where the Celsius and the Fahrenheit would be the same number. That's -40. Just plug that into the formula, it'll just give you -40 again. Okay, so 45 degrees Celsius, on the top of your head, is that hot or cold compared to your usual human experience? Sorry.
Oh, wait, you said.
45, yeah, we're going to start from the top and go down. 45 Celsius, is that hot or cold? That is very hot, because that's room temperature, so that is very warm. I have Canadian friends, and they will frequently complain about a 30-degree day in the middle of summer. And I always have to do a quick double take to remind myself that 30 Celsius is like nearing 100 Fahrenheit. Now, 45 Fahrenheit, hot or cold? That is cold, because that's lower than our average temperature for Fahrenheit. Meanwhile, 45 Kelvin is colder than anything that will naturally exist on this planet. Again, if you ever feel anything remotely near that temperature, you are a timesicle. So don't go looking for it. So just make sure your work lines up with these numbers. In general, when I'm grading tests and such, I'm not too particular about when you get the exact number. There's a certain degree of rounding that is acceptable across all platforms. But if WebAssign gets on to you about that, if you do your math, you have a number you think is right, and WebAssign keeps saying it's wrong, it might be a rounding thing, and I can check and make it do the right thing.
How do you go from Kelvin to Fahrenheit?
You kind of have to bounce between Celsius. Although, you know what? This is a math-based class. We can combine those two formulas together real quick. TK equals TC minus 273. Wait, what? No. I confuse myself far too often.
That's right.
This is, okay, thank you, sorry. Sometimes I just need that validation. Meanwhile, so, okay, this is TK equals TC. So what we would ideally like here is TC equals TK minus 273. Meanwhile, we also have TC is equal to 5/9 TF minus 32. Sorry?
This is a lot of time.
It is, but I'd like to do this with you really quickly because this type of a method is going to show up periodically. It probably did in your last class too. This is a situation that I call two equations and is it 3 unknowns, technically? Yes. Point is, we have 2 equations that each have 2 unknowns in them, but one unknown is the same across them. So we can set them equal to each other to cancel that out, and we just have the 2 unknowns left. So TK minus 273 equals 5/9 TF minus 32. So technically, TK equals 5/9 TF minus 32 plus 273. further note, my handwriting is awful on a good day. And the quicker I write, the worse it gets. So I apologize for that in advance. No, not in advance, it's happening now. I'm going to apologize for that the entire period of time that you were working with me. You know what, I kind of want to solve that. I kind of want to get it to something more simple. Okay. So, simplify this, okay. This is the one still. Simplify this one line further. TK should be equal to 5/9 times TF plus 255.22.
Why, on like there, would you not put, the TF in parentheses? And like on the first, like it's not up there, like going from, like solving for Fahrenheit with the TC plus 32 not being in parentheses. That's not up there.
So, okay, you were right. I kind of skipped a few steps because I was in a hurry.
Whoa.
Right.
Oh, yeah.
Yes, I foiled the 5/9 into here, which split this into 5/9 times TF minus 5/9 times 32. 5/9 times 32 is 17 and some change, and that's going to be a negative number. So negative 17-ish plus this gives this. And the 5/9 times TF, that's a variable, so that can't be reduced any further yet. So feel free to write that one down. As you're writing it down, one quick point to make about temperature scales. I mentioned that temperature is a comparative measure. It can tell you the comparative thermal energy level of an object, but temperature alone will never be an absolute indicator of how much thermal energy an object has. For example, let's look back at this ice cube. It's okay, if this was actual size, this would be a pretty big piece of ice. But we know, let's say it's at 0 degrees Celsius. Would that have more or less thermal energy than this bigger block of ice at the same temperature? They're at the same temperature, but does that mean they have the same energy level?
Yeah, because the mass would be.
Very good. So everyone who said no, well done. And the reason is this just has more mass in it. It has more particles that all need an amount of thermal energy to be at 0 Celsius. If it didn't have that much energy, it'd be colder than that. So temperature is not an absolute indicator of thermal energy level because 1 cup of hot coffee has less thermal energy than the entirety of the Arctic glacier because it's just so big. So temperature measures average thermal energy level across, average kinetic energy of an individual atom inside of an object. So if these two ice cubes are both at 0 Celsius, and we were to look at one water molecule in each of them, they should have the same kinetic energy level. But this has more atoms that all have that same kinetic energy level, so this one just has more total energy in it. Which is why it would take more thermal energy to make it melt. So, temperature is a relative scale, and it doesn't directly tell you thermal energy level. That will come later. Now, there's something I want to make sure that you guys see so that you can utilize it tonight if you're doing your homework. I just want to get the concept in your head so we can begin here tomorrow. I'm sorry, you guys look at me. Every time I see you writing, I just get nervous watching these slides. So, we've mentioned that the more thermal energy something has, the more its particles are going to be moving. The more its particles move, they're naturally going to be faster, but that means that they're also going to collide more. And if they're colliding more, those particles tend to naturally drift further apart. I know this is a drawing, but you notice sort of the increasing size of the little atom cluster. So as a general rule, the warmer something gets, the bigger it gets. Because ever so slightly, on the atomic level, its particles collide with each other more and drift slowly apart. You've seen this in your day-to-day life, because I assume most of you have seen ice melt. Technically, when ice melts, the block of ice gets warmer, it expands slightly, its particles get further apart, and eventually they get far enough apart, where they can't hold a solid shape anymore, and they become water. Yes?
So like, you know how you put a can of Coke in the freezer, it expands, and that has to do with like the whole, just, I guess, formula and the ice and making it solid and it expanding, but,
Right.
so does that mean that when something's warm, it expands even more than when something freezes?
See, okay, so that's a very good point. When water turns into ice, that's sort of the one exception to this rule, one of the few exceptions to this rule. Typically, as you make something warmer, it gets bigger, and as you make something colder, it gets smaller. Ice is a weird exception because when water freezes, its particles take on like a crystal helix structure, and they lock in place. They are now locked into this structure, but they tend to be further apart when they do that. So when you go from water to ice, its volume does increase. That's one of the few exceptions to this general rule. But it's a good exception to be aware of because it makes life on this planet possible. If ice didn't expand on freezing, ice wouldn't float. Ice is less dense than water because it expands when it freezes. That means ice floats. That means it stays on the surface of the ocean instead of sinking to the bottom and raising the sea level unnaturally. So,
Wait, sorry, all right, and then, so when we're talking about like that rule, are we talking about like solid gases, like that?
in general, if you have some material and you make it warmer, it will expand. It gets a little funny at phase changes sometimes. Generally, phase changes follow the same rule. When something gets warmer, it expands. Like if you evaporate water, it takes up a much bigger space as steam than it did with water. There's only a few glitches, like the transition from water to ice and some other crystals that I know of, that cause that weird effect. In general, warmer means bigger. And we call this principle thermal expansion. And you don't notice thermal expansion too much in terms of things that aren't phase changes, because the effect of thermal expansion is usually very minor in the temperature range that human beings often define themselves in. But to prove the principle, I have with me up here, these are highly scientific tools that we refer to as a ball on a stick and a hoop on a stick. So, this sphere is just the right size to be able to fit through the ring. It just perfectly goes. Kind of catches for a second because they're exactly the same width, and then it'll go through. Just to prove the point before we break today, because I really like doing this demo. Light, 2 matches, and I am going to heat up the sphere. Use 2 matches because one just doesn't do it fast enough. There's that. So, we'll see I'll prove in a second that it is technically expanding, but you would never notice this expansion with your naked eye. It happens in nature, like it can be measured, but kind of like how you can measure how fast a snail moves or how fast a tectonic plate moves. It's happening just so slowly that the human eye can barely tell. But it becomes very important in places of high precision. You guys ready? And to prove that I haven't just got it stuck in there somehow, I have water to cool it back down. So, the warmer something gets, typically the bigger it gets. We're going to look into that math next time. I need to make that clock do just the time on the clock. So, thank you all. The class tomorrow, we will look at the formulas for thermal expansion and how the math of that works so that you have it and on your homework. Chapter 10, I foresee taking about most of next week too. So chapter 10 homework is presently due Tuesday after next, so we have all of next week to learn and then we'll move on. So you'll be looking at it as soon as you start, as soon as you finish it. Have a wonderful day. See you tomorrow. Weekend is time.
I thought the one was doing the 7th.
Sorry?
I thought the one was doing the 7th.
Tuesday after next.
I thought it was on a Sunday. But maybe it's changed and I lost track of it. 'Cause I didn't
Oops. Yeah, sorry about that. Okay. Yes, WebAssign says the 7th. My intention is actually the 9th, and I will adjust that. Thank you for telling me, because I didn't notice that. Have a good day.
Thank you.